Hello and welcome back to Hilbert Spaces, the video series where we talk about linear operators acting on complete inner product spaces. And indeed, in today's part 18, we will talk about the adjoint of such an operator. You should already know that for matrices from linear algebra, so you can see this video as the natural extension to infinite dimensions. However, before we write down the definition of this adjoint operator, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that as a supporter you can use the link in the description to download a lot of additional material. For example, there you find quizzes, PDF versions and books. And with that out of the way, we can immediately start by considering two Hilbert spaces x and y. This is the assumption we have here, so in general we also have two different inner products. And now what we will consider as well is a linear operator t from x to y. And as always, this should be a bounded linear operator, which means that the operator norm of t is finite. And now I can already tell you that the adjoint of t is a linear bounded operator from y to x. And usually this adjoint is denoted by t star. And as already mentioned, from linear algebra you might already know this star notation. There it just means you have a matrix where you take the transpose and the complex conjugation together. And now on an abstract level, this adjoint operator does exactly the same thing. The only difference is that we don't talk about finite dimensional matrices, but about general abstract linear maps. And now instead of giving you a definition for t star, I can immediately start with the proposition where we can prove that this t star operation is well defined. More precisely, we have to show that there is only one possible operator that satisfies the conditions we want to have. But first let's write down the assumption again. So we have two Hilbert spaces x and y and a linear bounded operator t. And there please recall from functional analysis that bounded means that the operator norm of t is finite. And you should know that the operator norm is written as a supremum. And to keep it short, we can go through all normalized elements in x, and then we just calculate the norm of the image tx. So this is well defined because the supremum always exists in the real numbers, but it should also be finite. So here we have all the assumptions we need, and under these we can conclude that we have an operator going from y to x as well. And moreover, besides the existence, we also have uniqueness in the sense we will explain now. So clearly t star is not just any operator from y to x, but it also should satisfy something in the inner product. And you might already know that it's just shifting the operator from one side in the inner product to the other side. So more concretely, here on the left hand side we have the inner product y with tx. And this should be the same as t star applied to y on the left hand side. So we have t star applied to y with x in the inner product. And this also means that here on the right hand side we have the inner product in x, and on the left hand side we have the inner product in y. And now obviously we want to have this equation no matter which vectors x and y we choose. And now the result we have here is that such an operator with this property always exists, and it's uniquely determined by the property. And by knowing the last video, you might already guess that this essentially comes from the Riesz representation theorem. So this is the important part that goes into our proof now. And now the first thing we have to clear up is what is t star y when y is given. So first, just the mapping from y to x should be well defined. And with regard to the last video, the first thing we can do is to define a linear functional L. And this one should depend on y, so I put y in the index. But it should be a functional defined on the Hilbert space x, so we put in a vector x. And then the definition we choose is the left hand side here. So in x here, this is clearly a linear functional, and it's also bounded because we can use our Cauchy-Schwarz inequality. So just to be clear, Cauchy-Schwarz will tell us that this absolute value here is always bounded from above, namely by the norm of y and the norm of tx. And with that we already know if we go to the supremum here, we get a finite number for the operator norm of Ly. And now, because we have a bounded linear functional Ly defined on the Hilbert space X, our Riesz representation theorem can be used. It simply guarantees us that there is exactly one vector in X that represents the whole bounded linear functional. And to make this relation clear, let's put Ly into the index of X. And representing means here that Ly is given by an inner product where this vector xly is on the left hand side. And to keep it short, I will introduce this informal notation where we just have the left of the inner product. Which just means if we put an x into our functional, then we get the full inner product out. And please note, there we have the inner product in the Hilbert space X. Okay, and now you see, with the existence of such a vector xly, we have a definition for our vector t star y. Indeed, the outcome of t star y should be just the vector xly. And the whole thing here is well defined because it works for every vector y without any ambiguity. Hence the map t star is already well defined, and in the next step we have to show that it is actually a linear one. There we have two properties to show, and let's start with the addition. So we take two vectors y1 and y2 from y. And now, since t star is defined for every vector in the Hilbert space y, it's also defined for y1 plus y2. And what we know by the Riesz representation theorem tells us that we can use that in the inner product. So the right hand side x here is in the Hilbert space X and arbitrarily chosen. And now, by the definition of our new map t star, we know that this vector here on the left is given by such a vector x with an index. And therefore, the whole thing is actually just such a special bounded linear functional Ly. Or more precisely, now we would have y1 plus y2 in the index. However, now we can use the original definition of the linear functional, which gives us an inner product in y. And there you already know, in this case, the first input is y1 plus y2. And then we don't have a problem because the inner product is definitely additive in both components. So we can just write it with two inner products, one with y1 and the other one with y2. And then by definition, we just have that these two things are our linear functionals again. So just the addition of two linear functionals, but there we also already know that this is exactly the definition of t star y. In other words, now we can write it as two inner products in X again. And of course, this helps us a lot because we can use the linearity of the inner product in X again. So we only have one inner product, and there we have the sum of the two images. So this is almost what we want to have, because now if you compare it to the original form, we have pulled out the addition. However, we also want to get rid of the inner product, so let's subtract the result such that we have 0 on the right hand side. And then of course, as before, we can also pull in the minus sign because our inner product is additive in the first component. And now you see what we get with the whole calculation here is an orthogonality in the Hilbert space X. Namely, this vector on the left hand side lies in the orthogonal complement of X, where we already know that this is only the 0 vector. Therefore we get our result here, this is the 0 vector and the inner product is gone. So the first part of linearity is shown, we can pull out the addition. And for the second part, we need to show that we can pull out a scalar. Hence, let's fix a lambda in f and a vector y in y again. And then essentially we do the same thing as before, so we consider t star lambda y in the inner product. And also that one, by definition, is given by the linear functional L. Which again means that we have an inner product in the vector space y. And there, as before, we want to pull out what we have inside the first component. So now we pull out this lambda factor, which means it gets a complex conjugation. So actually not really a problem, but something we have to keep in mind. Moreover, the only thing that remains next to it is our linear functional again. So now we have Ly applied to x. Which also means we can go back to t star with the inner product in X. And this is really nice because, as you can see, in the last step we can just pull in our lambda factor again, and this complex conjugation will go away. And with that we have it, because now, as you can see, we can do the subtraction again and argue with the orthogonal complement again. And then what we get is just the homogeneous property, so the second part of linearity. So please keep that in mind. This one is to prove that T star is a well-defined linear map. So the existence is almost done, and we just have to show that T star is also bounded. This is not hard at all, because we just have to calculate the operator norm. And as already mentioned at the beginning, the operator norm is always given by a supremum. So we just have to check if there's an upper bound for the norm of T star y, where y is normalized to 1. However, now we talked about this many times, T star y is just the linear functional defined on x. And indeed, the Riesz representation theorem tells us that the norms stay the same, so this one is just an operator norm of L. So more concretely, the operator norm of Ly. Hence also this one is written as a supremum. But there we have the supremum over x, and what we put in is Ly of x in the absolute value. And in fact we have talked about this before, because this absolute value is bounded by the norm of y times the norm of tx. This was just a simple application of the Cauchy-Schwarz inequality. And obviously this is good enough for us because we just want to have an estimate anyway. And there you immediately see that the supremum over y is not necessary at all because it just gives us 1 anyway. So only the supremum over x remains, and by definition this is exactly the operator norm of t. Hence T star cannot have a larger operator norm than t. And therefore T star also has to be bounded. And in fact, in the next video we can also show that we actually have equality here. This means using the star operation does not change the operator norm. And now regarding the existence of T star, we see we are done. We always have this bounded linear operator we call the adjoint. Moreover, the uniqueness is also done because there was no choice at all how to define T star. In fact, this comes immediately from the uniqueness in the Riesz representation theorem. So maybe let's quickly recall the point there. This one was the defining property, and on the left hand side we have a linear functional Ly. And this functional y is uniquely represented by the vector xly. So we have this equality for all x in x, which means we can bring this to the other side and do the whole argument with the orthogonal complement again. So the implication is simply this vector t star y has to be the vector xly. There's simply no other possibility, and the uniqueness is definitely done as well. So this finishes the whole proof, and our T star for every operator T is defined. And just to keep it clear, let's write it down that this well-defined T star operator is called the adjoint of T. So this is the important name you should remember. We say adjoint and we mean this operator T star. And as already promised, in the next videos we will do some more calculations with this nice adjoint operator. So I really hope we meet there again, and have a nice day. Bye bye.